We're introducing Swyft. Swyft is a set of algorithms and a software prototype that we've prepared for you. It exists in the class of likelihood-free and simulation-based inference algorithms. Where Swyft is special is that it is incredibly simulation efficient by estimating the marginal posterior, any marginal posterior of interest. A marginal can be used to bound the parameters for some inference problem. Also, marginals are used in visualizing the higher dimensional posterior in something like a corner plot. Why would you focus on marginals? Well, a marginal eliminates the complexity of higher dimensionality. The curse of dimensionality is reduced. Also, sometimes things like multimodality are reduced. It makes it very easy to target regions of parameter space that are valuable or relevant. And how we've set things up, it becomes natural and simple to reuse samples. Therefore, Swyft really shines when your simulator's slow, or it's too complicated to write down the likelihood for your simulator, or you have a large number of nuisance parameters. Let's break it down. The first algorithm we've introduced is nested ratio estimation, a method inspired by nested sampling. Consider some x naught that you're interested in, and you want some arbitrary marginal posterior. We construct a sequence of rounds. At every round, all one-dimensional marginals of theta are estimated. Each of those one-dimensional marginal posterior estimations are over the same underlying posterior, and each of them are used to constrain the prior in the next round. Once this is done, you have zeroed in on a constrained prior that is particularly relevant to your x naught of interest. Now, to access the marginal posterior of interest, you merely train another neural network to estimate the likelihood ratio and give you the posterior. Swyft is particularly useful when the simulator is the bottleneck and not the neural network training. When this is the case, we've optimized for it by setting up the regime such that we never reject simulations and we reuse previous ones. All of the simulations that you use to constrain your prior to the relevant region can then be utilized again when estimating the marginal posterior of interest. We do this by applying an inhomogeneous Poissonian point process. Now let's look at our examples. On the left is ours, and on the right is multinest. You can see that qualitatively and quantitatively they agree. But when it comes to the amount of simulator runs that were necessary at first, ours is an order of magnitude faster. And then when it comes to follow-up studies, where multinest would need to start all over, we already have many simulations in the cache, and we are 2 orders of magnitude faster on follow-up studies in terms of simulation runs. There's a few things that are unintuitive about estimating marginals, and one of them is the scaling in an egg box-like problem, where as the dimensionality increases, the number of modes increases exponentially. In multinest, you get the expected behavior, where the complexity in terms of number of samples required for convergence increases exponentially. But since we're interested in the marginals and not the total posterior, we get this effect that after a certain number of modes, it's nearly constant in samples required. If you're interested, please come visit our poster. I'm excited to talk with you.